Hi, my name is Binghao Wang. I'm a graduate student from the University of Southern California. Today, I'm going to discuss the effect of thermally activated friction on rupture dynamics. A wide spectrum of fault dynamics has been observed in various tectonic settings, including seismogenic and aseismic slope events, earthquake swarms, and regular large earthquakes. A fundamental goal of earthquake physics is to establish the constitutive laws that enable this wide range of behaviors. The physics of dominantly aseismic slow slip events and of large earthquakes is relatively well understood in the framework of rate and state dependent friction in isothermal condition. However, the physics of tremogenic slow slip events and the occurrence of seismic swarms is still poorly understood. Here, we explore to what extent can this wide range of fault slip behaviors be explained by rheological effect considering non-isothermal conditions. The frictional response of faults is thermally activated, with any sudden increase in temperature causing an immediate reduction in shear stress followed by a time-dependent recovery. Even though any temperature increase reduces the frictional resistance, it also accelerates heating, which leads to strengthening. As a result, the frictional response at steady state can be temperature weakening, temperature neutral, or temperature strengthening, depending on the thermodynamic parameters. The thermal activation of friction may play an important role in fault dynamics because of shear heating. These effects can be captured by a constitutive friction law, where temperature is a dynamic variable, controlled by the activation energy Q and the activation enthalpy H for the direct and evolutionary effects, respectively. The steady state behavior is captured by the parameter BH minus AQ. When BH minus AQ is positive, the response is temperature strengthening, which is the stabilizing effect. Because an increase of velocity and of temperature have opposite effects on friction, velocity weakening is often associated with temperature strengthening and velocity strengthening with temperature weakening at steady state. The potential for thermal instabilities in velocity strengthening region has been explored in previous work. The goal of this study is to explore rupture dynamics in a temperature strengthening, velocity weakening region. We consider a 1D fault embedded in a 2D medium. The fault includes a seismogenic zone with velocity weakening, temperature strengthening friction, surrounded by a velocity strengthening, temperature weakening region. The temperature evolution is controlled by shear heating and heat diffusion within a membrane diffusion approximation. Including the temperature effects, the governing equations give rise to an additional 4 non-dimensional numbers. RH controls the amplitude of the temperature strengthening effect. 2 other parameters are ratios of timescales for shear heating, heat diffusion, and contact erosion. The non-dimensional analysis largely reduces the independent dimensions of the parameter space and guides us through the numerical exploration. We conduct quasi-dynamic simulations to solve the system of equations. We explored the impact of the thermodynamic variables on the seismic cycle, given how they affect the non-dimensional numbers. Here are the results. First, temperature strengthening produces fast ruptures with different rupture styles, crack-like ruptures and pulse-like ruptures. Limited temperature strengthening gives rise to crack-like rupture with bilateral and unilateral propagation. We also find mixed mode ruptures exhibiting both pulse-like and crack-like components. Varying the temperature dependence produces different types of pulse-like ruptures, decaying pulses, steady pulses, and growing pulses. A transition from crack-like to pulse-like ruptures can also be found in isothermal friction for increasingly unstable faults, but temperature strengthening produces a wider range of rupture styles. Considering all the simulated events over multiple cycles, There is a transition from crack-like to more pulse-like ruptures as temperature strengthening becomes stronger. As we can see from this top panel of the right figure, the y-axis is the crack degree, a measure of how close an event is to an ideal crack-like rupture. The x-axis is a thermodynamic parameter in the seismogenic zone. Each dot in the figure represents an event. The size is proportional to the moment, and color codes peak velocity. Each column represents all events over multiple cycles in a given input parameter setting. The lower panel shows that the largest event in the simulations becomes smaller as temperature strengthening increases. Also, the rupture complexity increases with more pronounced thermal strengthening. We start to have clusters of smaller ruptures instead of a simple characteristic large event in an individual cycle. For stronger temperature strengthening, the behavior becomes more unique. Many events break a small fraction of the seismogenic zone at a time. We can see from the velocity history that these events are clustered in time and space without any characteristic large event that could be recognized as a main shock. These are the characteristics of seismic swarms. We suspect that the strong temperature strengthening effect in the seismogenic zone precludes large earthquakes by limiting the size of seismic events, producing sequences of small events instead. The simulation also showcases propagation of swarms through the velocity weakening region within a cycle. The seismic moment released is comparable to the aseismic moment, suggesting a strong interplay between fast and slow processes. This is consistent with observations that some earthquake swarms are accompanied by aseismic sleep. A wide range of recurrence patterns for seismic swarms can be obtained within the model. We can control the recurrence time of earthquake swarms or any other type of force-sleep behavior by changing some physical parameters while keeping the non-dimensional numbers the same. Here we covary the timescales of shear heating and weakening to obtain seismic swarms with different frequencies. The model predicts persistent earthquake swarms with recurrence time around 10 years, intermittent swarms with recurrence time of 25 years, isolated swarms with a 50-year return period, and even black swan earthquake swarms with recurrence time of the order of 100 years. With even stronger temperature strengthening effects, the model produces tremogenic explosive events. They are bursts of even smaller magnitude events that cluster in time, most of which occurring aseismically. These events incorporate small earthquakes that represent only about 27% of the total moment. Every rupture sequence involves multiple re-ruptures of the same location, which is one of the characteristics of tremors in nature. As far as we know, this is the only model that produces tremor-like signals within a single homogeneous asperity. Besides the temperature-related parameters, we can also explore the non-dimensional numbers that already emerge in the isothermal case. For example, the RU number, which is proportional to the ratio of the asperity size over the nucleation size. With temperature strengthening, aseismic slow-slip events occur for a wider range of RU numbers than for isothermal friction. Considering thermally activated friction may explain the spectrum of slow-slip events, from aseismic to seismogenic to tremogenic slow-slip events. The competition between direct thermal weakening and time-dependent thermal strengthening is captured by the parameter BH-AQ. Varying combinations of thermodynamic parameters H and Q lead to different force-slip behaviors, including crack-like ruptures and pulse-like ruptures, seismic swarms, and tremogenic slow-slip events. The phase diagram on the right summarizes some aggregate features, including maximum moment, minimum crack degree, peak velocity, and seismic moment ratio. All these quantities change systematically as we tune the parameters. Moreover, this transition is closely aligned with contours of BH-AQ, indicating that BH-AQ is the more important dimension in H and Q 2D space that controls the rupture characteristics. As a summary, we explored the effect of thermally activated friction on force-slip dynamics over multiple seismic cycles for a velocity weakening temperature strengthening patch. A wide spectrum of force-slip behaviors from fast to slow, seismic to aseismic, characteristic to cluster events can be explained by temperature-dependent friction, including crack-like and pulse-like ruptures, earthquake swarms, concurrent slow events and tremors, and slow events of different styles. Various aspects of force dynamics are mainly modulated by the parameter BH-AQ. The temperature strengthening effect can contribute to complexity of earthquake rupture behavior in a velocity weakening patch and may be key to explain a wider spectrum of rupture dynamics.